At noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast? How fast is the distance between the ships changing at 4 p.m.? From noon to 4 p.m. And first, we would draw a diagram. Always try to draw a diagram if possible. East, west, north, and south. Ship A is 100 kilometers west of ship B, and so as of now, ship B is on the right and ship A is on the left. The distance between them is 100 kilometers. A is west of ship B. Ship A is sailing south, and so ship A is going down south at the rate of 35 kilometers per hour, and ship B is sailing north. Ship B is going up at the rate of 25 kilometers per hour. It is worth pointing out that this distance keeps changing, and the distance keeps changing because the ships are moving. Therefore, the distance between the ships is also changing. Let this distance be z. This is a variable. We are looking for dz dt when t is 4 p.m. So how do we relate all of the given information to form an equation? If we were to let this distance be x and this distance be y, how do we relate x, y, z, and then 100? We can work with two right triangles. 1, 2. We can let the distance be t, and this is therefore 100 minus t, but then we would have to work with two equations, which is fine because the distance z is z1 plus z2. However, alternatively, we move the distance y so that it is aligned with the distance x. We still end up with the same distance z if we do so, meaning at this y going up, this y going up at the same time as well. So this distance is the same y. And so by looking at this, we simply have 100 squared, which is the horizontal distance, plus x plus y squared, which is the vertical distance, equals z squared. We avoided working with two triangles. Now we're looking for dz dt, so we would differentiate both sides of the equation implicitly with respect to t. D dt of 100 squared plus d dt of x plus y squared and d dt of z squared. The derivative of 100 squared is 0. The derivative of a squared is 2x plus y, and then we multiply the derivative of the inside, which is the derivative of x with respect to t is dx dt. The derivative of y with respect to t is dy dt, equals 2z dz dt. Implicit differentiation. Technically, This x is a function of time because x is the distance that ship A has traveled. This y is also a function of time. Remember that ship A traveled at a speed of 35 kilometers per hour starting at noon, and so after 4 hours at 4 p.m., the distance it has traveled is 140 kilometers. Similarly, ship B is traveling at the rate of 25 kilometers per hour. After 4 hours, it would travel 100 kilometers. dx dt is the rate at which ship A is moving. This is 35 kilometers per hour. And dy dt is the rate at which ship B is moving. This is 25 kilometers per hour. And so we have x, we have y, we have dx dt, we have dy dt. We still need to find z, but to find z, we can just simply use the big right triangle. This horizontal distance is 100. We know that at 4 p.m., y is 100 and x is 140, and so the vertical distance is 240. At that particular moment, z squared is the square root of 100 squared plus 240 squared, and so this is 260. Now we have z. We just need to isolate dz dt. It is probably easier if we plug in the numbers before isolating dz dt. The factor 2 and 2 canceled out, so we don't have to keep rewriting it. X is 140, y is 100, dx dt is 35, dy dt is 25, z is 260, and dz dt is what we're looking for. This is 240 times 60 equal 260 dz dt. Isolating dz dt, we get 240 times 60 over 260, and this should give us 720 over 13. This is roughly 55.4 kilometers per hour. And so exactly at 4 p.m., the distance between the two ships is changing at a rate of 55.4 kilometers per hour. They are moving further apart.